In this section, we are talking about the variance of these slope coefficients, and we saw that the variance of any coefficient, it depends on three factors: the error variance, total sum of squares, and the r squared, which we get from estimating one particular x or explanatory variable on other explanatory variables. And we saw that in order to decrease the variance of any beta parameter to get more precise estimates of these beta coefficients, we have to decrease sigma squared, that is the error variance. We have to increase the sample variation in the explanatory variables by increasing the number of observations in our sample. Or we have to decrease the correlation between these x variables on the right hand side, and if we do any of these three, we'll get a minimum variance. Also note that if we are interested in this beta 1 coefficient, and we are interested in the impact of this x1 variable on y, and we are controlling for other factors by including other variables x2 up to xk, then the correlation between, say, x2, x3, x4, it may not be very problematic. All we care about is the correlation between this x1 variable, which is our variable of interest, and any of these other variables. The problem is known as multicollinearity. That is, if there is a very high correlation between these x variables, specifically high correlation between x1 and any of these x variables, it's gonna be called multicollinearity, which is problematic. One way to judge multicollinearity between these variables is to use variance inflation factor, or VIF, which is calculated as 1 over 1 minus r squared j. So this r squared j is again the r square that we get from regressing our variable of interest on other variables in the model. It is not the same r squared that we get from this equation. And again, here our variable of interest is x1, and we are interested in knowing this beta 1 coefficient. So we want to know what is the variance inflation factor for x1. And in order to do that, we will regress x1 on other variables and then get this variance inflation factor. This formula is directly related to the formula of variance that we got from here. What we are trying to do is we are splicing out 1 minus r squared from here. Hence we'll have variance of beta j, that is our variable of interest, equals sigma squared over total sum of squared from the jth variable of interest and VIF from the jth variable of interest. Variance inflation function is the factor by which variance of beta j is higher because xj is not uncorrelated with the other explanatory variables, these explanatory variables. And what we want to do is we want to minimize this variance inflation function. We want it to be as smaller as possible. If VIF is greater than 10, multicollinearity could be problematic. And this 10, it's an arbitrary number, and it arises when r squared is greater than 0.9. So this r squared, if we regress our variable of interest on other variables and get r squared, which is above 0.09, that is, this variable is highly collinear with these variables, then we'll get a variance inflation function which is greater than 9. This statistic may not be very useful. It has a very limited use, but you can use this for your own curiosity and to learn more about your data. All right, see you in the next video. Bye bye.